Hi there, welcome to this video. This is 8-2 and we are going to talk about particle motion, also known as rectilinear motion, and we're going to be revisiting this concept that we talked about in Unit 4, the contextual applications of derivatives, but adding in the knowledge of integration. Okay, so what I want to do is I want to go ahead and revisit particle motion for you and just give you back that overview. The big idea is that we will talk often about the position of a particle, and sometimes you'll see these formulas, or these functions, x of t or s of t. Sometimes that's the position. And then the derivative of position is the velocity. So we'll talk about velocity, and oftentimes velocity is what is given. And in a lot of, or most of the examples today, you will see velocity. And then lastly, the derivative of velocity is acceleration, and that is a of t. So if the derivative of position is velocity and the derivative of velocity is acceleration, how can I go the other direction? How can I start with velocity and find position? Maybe an antiderivative, maybe an integral. Okay. So that's the whole idea here, is that we're going to go ahead and work with some of these contextual problems, and we're going to integrate integration. Okay, so let's revisit some big ideas because it might have been a while. I want to talk about speed. Remember that speed is just the absolute value of velocity. Okay, so if you're ever asked about speed, it's the absolute value. But if you're ever asked if the object is speeding up or slowing down, speed increasing or speed decreasing at a specific value, what you need to do is you need to look at the velocity and the acceleration. Look at the velocity and look at the acceleration. If they have the same sign, speed is going to increase. It's going to increase. So you can speed up in a positive direction, or you can speed up in a negative direction. Okay? But if they have opposite directions, opposite signs, I should say, then speed is decreasing. Okay. Additionally, we can talk about the direction of motion of a particle. How do I know if an object is moving to the right? Well, its distance is going to be increasing, so therefore it's going to have a positive velocity. So v of k is greater than 0 if we're talking about a specific time k. And I know it's going to the left if the velocity is negative. If velocity is negative, then it's moving to the left. Well, how do I know if it changes sign? Well, the velocity is equal to 0, and then you have to see where does it change signs. That's very important. We change from positive to negative. That indicates a change in direction. Okay, so those are just some recap on particle motion, and I want to tie particle motion into what we talked about in the last lesson, 8-1, which is the average value of a function. If I have an interval a to b, the average value of a function, again, what we talked about yesterday, or in the last lesson, was 1 over b minus a times the integral of the integral from a to b of f of t dt. This is the average value, or the average height of the function. Now, sometimes the AP test will they'll ask for an average value of a function, or an average velocity, but then sometimes they ask for an average rate of change, or they ask for the average acceleration given the velocity. So how can I tell this new average value formula that we just defined yesterday versus average rate of change? How do I not get these mixed up on the AP test? Well, it's very, very straightforward. If they ask you to find the average of an equation that's given, if they give you v of t, and they say find the average velocity, you're going to use the average value function. Number 2, if they ask to find the average rate of the given equation, so say they give you v of t, and now they want all of a sudden v prime of t, or they ask for a of t. That is the rate of what they give you, so that you're going to use the average rate of change equation. Okay, so just wanted to talk about that. Let's go ahead, let's find some of these things. So example number 1, very, very straightforward. Given the velocity is equal to t squared sine of t, we're going to go ahead and do some things with this. So the first thing they say is find the average velocity on the interval. Okay, well, again, it's average velocity and they gave me velocity. So I'm going to use the average value function that we developed yesterday. 1 over 4 minus 1 times the integral from 1 to 4 of v of t dt. Now, we are going to use calculator, so if you have a calculator, please pause, grab your calculator, and oftentimes these particle motion questions are questions 1 or 2 on the AP exam. So what I recommend doing right away on these, when you read these, is go ahead and define your function. So menu, actions, and I'm going to define v of t. So I'll say, okay, v of t is equal to, and I think it was t squared times sine of t is what it was. Okay, hit enter, boom. There my function is defined. Okay, so now I want 1/3. I want 1/3, 1 minus 1 over 4 minus 1, that's 1/3, okay, times the integral. So I'll go integral, you can go next to the book here, or again, menu, calculus, integral, and we're going from 1 to 4, and then our function is v of t dt. There's a value. I'm going to go ahead and hit Control Enter to approximate, and we get 0.29111. So I'm just going to say this is equal to 0.291. Okay. All right, now find the average acceleration. Do you see how this is the rate? It's the rate of what's given, the rate of velocity. So here I'm going to use the average rate of change formula, v of 4 minus v of 1 over 4 minus 1. Now, the great thing about these problems is they're going to have you use that same function over and over and over again. So I've already defined it. I know it's v of, and I'm just going to say, okay, what's v of 4 minus v of 1 divided by 3, 4 minus 1. I hit enter, got to go ahead and approximate it, and we get negative 4.317. Okay, so there's my answer. Make sure you write this down. This is very important on the AP test. You can't just write down the answer and have the answer magically come to you. And I know it magically comes to you from your calculator, but the reader, the grader, needs to know that this is what you entered into your calculator. So write this down. And then oftentimes too, I had students, funny things go on with their calculators. They're not getting the same answers that everyone else is getting, even though they entered something in. So there's like a slight error, something's wrong. If you write this down, you're at least guaranteed to get 1 point, that you can earn partial credit on some of these problems. Okay, so next, I want to go ahead and talk about a couple of different ideas that we haven't talked about yet with particle motion, and that is the idea of total distance traveled. We have a particle that is moving in one direction, either on an x-axis or a y-axis, and it's changing direction, and sometimes they ask, what's the total distance traveled? What's the total distance that particle traveled? Well, again, in order to get the position, the total, right, the accumulation of the velocity, you're going to integrate from whatever limits they give you. You're going to integrate the velocity. Now, they want the total distance. Now, when we go to the left, okay, that changes, and that is now a negative value. Well, we want that to be positive, so we're going to add absolute value. So the absolute value of v of t dt. Now, if they just ask about displacement, like say, okay, here's my particle, it's moving over here, and then I move back. They want the displacement. Well, the displacement was between here and here, roughly. Okay, so now it's the same formula as total distance, but I don't have the absolute value. Okay, because that negative is going to take away the position, and it's just the displacement of my object. So, and you can write this down too. This is also written as x of b minus x of a. Okay, that's just the final position minus initial position. Okay. Now, something else that they can ask too is, what is a final position given a different initial value? And I like to just let this be known as this is the same thing as start plus accumulation. So whenever they give you an initial value in one of these problems, just note, hey, that's usually an initial value that I'm going to go ahead and need to use, okay? All right, so total distance traveled, displacement, and then final position or position of an object. We're going to go ahead and look at these. Okay, so back to the same example that we were working with. Find the total distance traveled over the interval 1 to 4. So if I want the total distance, again, that's just the integral from 1 to 4 of the absolute value of v of t dt. So I'm going to enter that into my calculator. I want the integral from 1 to 4 of the absolute value. Absolute value, again, for TI Inspires, right next to the book here, you have absolute value. And I want the absolute value of v of t dt. I hit enter, and there is the total distance that this particle has traveled on that interval 1 to 4. So 10.419. 10.419. Okay, find the displacement over the interval. Well, that's the same thing, but I don't have to make sure my velocity is always positive. I'm just going to go ahead and integrate from 1 to 4 and punch in v of t dt. Okay. There we go. 0.873. I don't know what the units are. They didn't give us units, but that's not much, you know. I guess this could be like kilometers, and then that would be fairly significant. But there you go. I'm integrating velocity. That's position. So the position at 4 minus the position at 1. That gives the displacement over that interval. All right, let's do some more meaty examples with this, something that you would see on a AP FRQ. So here is example number 2. This one is calculator active. Again, FRQs 1 and 2 do have access to the calculator. If it's number 3 or 4, 5, 6, you don't have access to the calculator, just for your frame of reference. So here, calculator active. For 0 to 3, the velocity of the particle moving along the x-axis is given by the equation v of t. It's known that x is equal to -4 when t is equal to 2. Okay, so I have my function. Right away, I'm going to define that in my calculator. And then 2, they tell us this: when x is equal to -4, t is equal to 2. What they tell you there is that the position at time 2 is equal to -4. So don't be confused. Sometimes that is confusing. They say x. X is usually our independent variable. But when working with particle motion, t is your independent variable. So x here, they're referring to position. Okay? All right, so let's go ahead. Let's define this right away in our calculator. So I'm going to go to, I'm going to start a new page. 1. You can change your definitions. You can do what's recall a define under here in actions. So again, menu, number 1, actions, and then I'm going to define. But if I had kept my old page, you could recall that definition and change it. I'm just going to start fresh. V of t is equal to 1.3 t squared minus 2.5 t to the power of 1.3 plus sine of t squared. Okay, you can pause me. That's the function if you need to. There you go. Done. Okay, I have it. All right, so let's see what they're asking. They say find a of 1. A of 1. Okay, well, a of 1, that's the acceleration at time t equals 1. That's the same thing as v prime of 1. Now, I write this down in my paper because I want the reader to know, hey, I'm going to take the derivative of velocity. So I can't just magically come up with the number and say, hey, that's a of 1. I got to tell them what I did, and I took the derivative of v at 1. So I'm going to go here, menu, calculus, derivative at a point. I want the value at 1. My variable, I'm going to change this to be t. So if you define it as t, make sure that variable aligns. So it says t equals, so the derivative with respect to t of v of t. So I'll just enter my function. Again, if you forgot what your function is, again, it's stored here underneath VAR. So, oh, V, that's what I called it for velocity. That makes sense. Hit enter, and there is your value, 0.431. And again, we're not given units. Okay, not too bad. Acceleration. That should be old news. All right, B, here we go. Here's the new stuff. Find the displacement of the particle on the interval 0 to 3. Okay, so what I'm going to do is I'm going to integrate. The displacement is equal to the integral from 0 to 3 of v of t dt. Okay, and I write that down because that's telling the reader, hey, I'm going to go to my calculator, I'm going to do that. So integral from 0 to 3 of v of t dt. And there it is. That's the displacement. Negative 1.128. Sweet. Not bad at all. This calculator's doing all this heavy lifting for us. C. Find the position of the particle when t is equal to 3. Okay, so I want x of 3. I want x of 3. Well, how do I get position? Oh, I have to integrate velocity. Okay, but note, they gave us an initial value. Didn't they say x of 2 was equal to negative 4? They did. They did. So I have the position at 2. You need that. Now I'm going to go ahead and accumulate the rest of the position by taking the integral from 2 to 3 of v of t dt. Okay, so I go ahead and do this, and let me just copy this down. Okay, and the calculator is going to do this work for us. This is just awesome. This is awesome. So one thing you can do, you can scroll up on the TI. I can just copy this down, and I don't want it from 0, and I want to add a negative 4 in front, negative 4 plus. I could have just subtracted 4. You get the same thing, but we get negative 4.047. Okay, and there is the position of the particle when t is equal to 3. All right, lastly, D, find the total distance the particle traveled. When they say total distance, you better make sure that all of that distance, if they went left, if they were negative, you better make that positive. So here, this is the absolute value from 0 to 3. Sorry, the integral from 0 to 3 of the absolute value of v of t dt. So we'll enter this. Go to our calculadora. Man, do you see how we're cooking? We're cooking through this. This question's lightweight. 0 to 3 absolute value of v of t. Okay. And there we go. 2.357. 2.357. All right, and there is the answer. Pretty straightforward, right? Okay, so that was easy. That was with the calculator. I want to incorporate these ideas into a non-calculator example. Here is example number 3. They say the graph below models the velocity of a bug in centimeters per second. That's important. Centimeters per second on the interval 0 to 13. Okay, so they say find v of 3. V of 3. Well, I'm given velocity. This is velocity that I'm looking at. So that's just the function value at 3, which happens to be equal to 6. And notice this is 6 centimeters per second. Centimeters per second. Centimeters per second. Okay, and then they want v of 11. Take a second, pause me. What's v of 11? Okay, and hopefully you got negative 2. Negative 2 centimeters per second. Did you include centimeters per second? All right, B, find A of 1, A of 5, and A of 9. Okay, so A of 1, I'm going to go ahead and look at 1, and this is V of t, so I want A of t, that's the derivative, that's the slope of this. So this slope looks like 2, so this is going to be 2 centimeters per second squared. Okay. All right, and then A of 5, you can go ahead and look at 5. That's 0. Flat line, 0 centimeters per second squared. And a of 9, looking at 9, that's -3 centimeters per second squared. Okay, so all of that actually included this next one, C. Where does the bug turn around? Well, this is when the velocity changes direction, when velocity changes signs, okay? So that happens at 9. We can say the bug turns around at t equals 9 seconds because, and here's your justification, they say give a reason, v of 9 is equal to 0 and v of t changes signs. And that last part is the biggest. You better have this. V of t changes signs. Okay, changes from positive to negative. That's how you know the bug turns around, changes direction. Okay, D. What is the total distance covered by the bug on the interval 0 to 3? Okay, total distance. So this is the integral from 0 to 13, and I want the absolute value of velocity, dt. Okay, I want the absolute value. So a couple of ways to think about this. You could go ahead and you could look at your graph right here, and we could mirror this point at 10. Instead of being -3, we could flip it up to be +3, and we can do this. And then there we go. We're just going to take the area underneath the curve of velocity. Another way, too, of thinking about this is, I know this area down here, right, and here is going to be negative. This is going to be a negative area. I can just make it positive, okay? So what we're going to do is we're going to take the integral from 0 to 9 of v of t dt, and then we're going to add the area from 9 to 13, but I want this to be the absolute value. I'm going to make that positive. Okay, so we'll go ahead. This is a graphical shape or geometrical shape. We can go ahead and cut this up into mini pieces. So let's split this up. And it looks like here we have a width of 3 times a height of 6. So we'll cut that in half. This is going to be 9 for that area. Here we have a width of 4 times 6, so that's 24, that section. And then here a base of 2 with a height of 6, so that's going to be 6. All that's 6. Okay, so that first area gives us 39. And the units on that, remember, I'm integrating velocity, which is centimeters per second, so that's centimeters, 39 centimeters. And then from 9 to 13, this area here has a height, or sorry, I'll do a width first. 1, 2, 3, 4. 4 times 3 divided by 2. So that's going to be -6. Okay, so plus the absolute value of -6, which gives us 45 centimeters. Okay, so there you go. There you go. That's a negative area right below the x-axis. All right, and then E, what is the displacement of the bug on the interval 0 to 13 displacement? So this is just the integral from 0 to 13 of v of t dt. And we already calculated this, right? The area under the curve from 0 to 9, that was 39 centimeters. And then we went ahead and calculated the area from 9 to 13, and this was a negative area. So what we're going to do is subtract that 6 centimeters, giving us a displacement of 33 centimeters. All right, hopefully in this video you went ahead and you learned about how we utilize integration to calculate total distance and displacement of linear motion problems, usually involving bugs, particles, people on bikes, people walking, and you got a refresher on our old information. Something I recommend doing, go ahead, look at some old FRQs, and you can just Google these. You can Google, 2015 AP Calculus AB number 3. Here's this one that we're going to work on in class tomorrow, so you can work on that. And you can also, I believe, up until I think 2021. You can find the scoring guidelines available online. And then example 5, 2016 AB number 2. This one's a calculator active one. Check those out, try those, give them a go, and then you can look at the scoring guidelines, see if you're right. Look at how the points are awarded, and ultimately do it just to have fun, because you know you're doing it to have fun. Don't we love calculus? I'll catch you in the next video. Peace out. Like, subscribe.